using a pencil on a piece of paper is, to me, one of the simplest forms of freedom that there is. Because look, you can draw anything you like, and there are no rules or limitations to what you can draw on a piece of paper. Well, that is, until I learned some geometry and realized that, well, actually, there are some constraints and rules to what you cannot do on a piece of paper like this. For example, a well-known one that I'm sure many of you know is if you draw a triangle, any triangle you like, no matter what kind of triangle you draw, big or small, the three angles on the inside of the triangle, let's see, how should it look? Maybe like this. These three angles will always add up to 180 degrees. And that is apparently a fact. Right? You cannot draw a triangle on a flat sheet of paper in this world such that the angles don't add up to 180 degrees. Well, I thought since this is such a simple rule, why not play around with it, right? Let's actually just draw a random triangle and just check if the angles actually do add up to 180 degrees. So here we go. Before I start, I will begin with a quick disclaimer that what I measure here, based on the imperfection of my measuring instrument and even the thickness in my pencil, actually also my camera is kind of right in my face in this poor setup here. So based on all these imperfections in our real world, I might not get the angles to add up exactly to 180 degrees in my measurements here, but they should at least be very, very close. With that said though, I will do the best I can to make accurate measurements. Let's see. Okay, what's this? This is just 1/45. 45, so that's 46. Okay, and then this one, let's say, this one is just 1 before 60, so 59. Okay, and then here, let's see, is that right? Am I getting it right? That is 75. Okay, 75. Alright, let's see. I got my calculator here. Let's see if they all add up. I realize my 75 is facing the wrong way. My apologies. 46 plus 75 plus 59. Make sure the camera can see this. Alright, let's see. Oh, look at that. 180 degrees. Like, seriously, isn't that beautiful? The fact that I can just draw any random triangle I like, measure its angles, and hit exactly 180 degrees, or sometimes 179 or 181, just based on imperfections, as I mentioned. But yeah, I think that's truly delightful, that these subtle things, I don't think they are appreciated enough. And also, obviously, there are many other similar things in geometry. For example, if you draw a right-angled triangle, I won't measure everything here, but as I'm sure many of you know, if you measure the side length here, the square of the length of this side plus the square of the length of this side will equal square root of length of the longest side. And even much simpler geometric configurations, such as two parallel lines, right, with the third line intersecting them, right, the opposite angles would be equal, these angles would be equal, and even almost trivially, right, these two angles would add up to 180 degrees. But nonetheless, it's the idea that when you put such geometric configurations on a piece of paper, you can't help but make these sets of equal or supplementary angles. And really, in essence, trigonometry is, in its most elementary form, trigonometry is just another piece of geometry. And they both rhyme, right? Look at that. In this video, my aim is to provide a natural introduction to trigonometry and to get us to gain a deeper appreciation of these subtleties in our world that I truly think is very delightful and very beautiful, that we can directly discover and interact with and play around with on a simple piece of paper with a simple piece of pencil. So let's begin by drawing two right triangles. I'm going to draw them such that one of them is relatively small and one of them is relatively big. Now please feel free, and I do strongly encourage you to follow along with me here and draw these triangles with me, right? Just to get in the spirit of getting your hands dirty and playing around with these concepts. Did my pencil just break? Oh, there's a dent in my table. Okay, so here is two right angles, and I'm going to draw the third. I'm going to draw the hypotenuse such that it's randomly orientated, but in the same way for both triangles. So let's do something like this, maybe. Okay, here's one right triangle, and here's a second, slightly smaller. Yeah, shoot, there's a thing in my table here, but that's okay. All right, here we go. Okay, so two right triangles. Here are the right angles. And you'll notice that they both have these angles in common, this angle in common, and they also both have this angle in common. You can come up with geometric proofs for these, and they're actually very similar to what we were just talking about. But in the spirit of just getting hands-on with it, I'm gonna just measure the angles and prove they are indeed the same angles. Okay, let's see, this one's 25, 26, 27 degrees. Okay, let's see. It looks like that also, I'm gonna have to extend this line a bit. Alright, here, now I can hopefully measure it. So yeah, so here we are. Okay, here we are. 30, 29, 28, 27. Okay. Great, we have two right triangles that share a 27-degree angle, and of course they also share these angles as well. They're the same, but for now, for this demonstration, we're just gonna worry about these two, this 27-degree angle. All right, and we're gonna start measuring some sides of the triangle here, trying to answer this very important question: how many times longer is the hypotenuse than this side that's opposite the 27-degree angle for each triangle? Okay, so, and that's a question I'll be repeating multiple times here because it's very important to the elementary introduction of trigonometry. Okay, let's see, this length here is roughly 3.55 centimeters. And of course, as I said before, my measurements will not be perfect, nor will anyone else's be with a simple piece of ruler like this in our world. So my final values will be slightly off, but hopefully not too much because I do try to do it as best as I can. 7.5, 7.6, 7.7, 7.8. Looks like 7.8 centimeters. Okay. Let's see. Here, how many times longer is the hypotenuse than this side, which is opposite the 27-degree angle? Let's see. Well, to answer that, we simply divide 7.8 by 3.55. We get roughly 2.20 if I round to 2 decimal places. So basically, what this means is that the length of this side, which is 3.55 centimeters, sorry, what I meant to say is the length of the hypotenuse, which is 7.8 centimeters, is 2.2 times longer than the length of this side. Okay? And let's do the same for the smaller triangle here. This length here is about 5, 6, 7, 8, 1.8, just about 1.8 centimeters, and the hypotenuse is that right, F4? That'd be pretty cool. Like 3.95. I'm gonna estimate at 3.95 centimeters. Okay, again, we ask the same question. How many times longer is the hypotenuse than this side, which is opposite the 27-degree angle? Well, 3.95 divided by 1.8 give us 2.19, rounded to 2 decimal places. So basically what we're trying to say is that the hypotenuse is 2.19 times longer than the side opposite the 27-degree angle. Okay, well, this is a bit of an interesting observation here, right? 2.19, 2.20, they're suspiciously extremely close. They're only off by 0.01. So a question becomes, is this a thing where if I draw a right triangle with one angle being 27 degrees, that the hypotenuse will always be around 2.19, 2.2 times longer than the side that's opposite the 27 degree angle? Or is this just a fluke? I'm just getting lucky here. Well, it's I think a third match of roughly the same ratio here should be very convincing. So I'm going to draw a third triangle that has a third right triangle that has a 27 degree angle. Okay, so to do that and to save some time, I'm just going to draw it right within this larger right triangle I have here, right? So look, I created a smaller, although this looks roughly similar to that, but I did it randomly, okay? So should be slightly different. Anyways, this is a right triangle that obviously has a 27 degree angle, right? Let me make sure this is indeed a right angle. Yeah, looks good. All right, let's measure the side opposite the 27 degree angle. And we will find that it is 2.1, I would say. Just about 2.1 centimeters. And the hypotenuse here, unfortunate placement of the 7.8. 7.8. Okay, but this smaller hypotenuse would be 4.5, 4.6, 4.7, 4.65 is my estimate. Okay, so for here, let's see, we have that 2.1 times what? 4.65 divided by 2.1 is roughly 2.21, rounded to 2 decimal places. So we see that the hypotenuse here is 2.21 times longer than the side opposite the 27 degree angle. Still very convincingly close to the two other ratios. It seems like there is a consistency amongst right triangles that if I were to draw a right triangle with one other angle being 27 degrees, I can't help but draw it such that that right triangle's hypotenuse is about 2.2 times longer than the side that's opposite the 27 degree angle. Now, to really solidify this idea and to try to prove whether this isn't a formal proof, right? But to get an intuition that this is indeed the case, let's try with a different angle, right? And see if we get a similar set of pattern. So here I will draw another right triangle, but this time with a different orientation of the hypotenuse to create some different angles. How about we do something like this? Okay, here it is. All right, and let's see. This is a right angle. Do it. And let's confirm this angle is indeed different from the ones we drew before. Okay. Is that 50 degrees? No, just a bit less. Looks like, can I say that's 49 degrees? I hope let's see. Okay, looks like it is between 49 and 50. Why don't we say it's 49.5 as an estimate? 49.5 degrees. All right. So let's see. Here we will measure the same lengths again and see how much longer is the hypotenuse than this side opposite the 49.5 degree angle. Here I see 5.4. I see 5.4 centimeters, and for the hypotenuse I see 7.2 exactly. 7.2 centimeters. All right, so now we ask the question, or rather we answer the question, how many times longer is this side than this side? Well, 7.2 divided by 5.4 equals 1.333. Okay, so we have 1.33 repeating over here, and that's kind of cool. So this is definitely not within the general range of ratios we had before with the previous triangles. It's significantly more different, and well, it would really mean something then if we find that ratios around this amount holds for right triangles with 49.5 degree angles, right? So, and I see that conveniently, I've drawn a second 49.5 degree angle here that is made by the opposite angles. So let's draw a second right triangle to really see if nature behaves in this way that we think. Here's a right angle. Okay, and let's measure this. So here the side opposite the 49.5 degree angle would be this one that I just drew. And let's see, it measures about 2.45 is my estimate centimeters. And as for here, the hypotenuse, we have 3.3 exactly. I'm gonna say 3.3 centimeters exactly. Alright, now with my measurements completely disorientated, let's see, 3.3 divided by 2.45 gives us 1.35, rounded to 2 decimal places. So in this right triangle, the hypotenuse is 1.35 times longer than the side opposite the 49.5 degree angle. And again, we see that, hey, look, suspiciously similar to this ratio here, resulting from the angle, right triangle with the same 49.5 degree angle. So I feel like there's something to be said about this. So it seems that for a right triangle, the factor by which the hypotenuse is longer than this side here that's opposite our angle of interest, this factor here, is always the same for the same angle of interest. For example, here the 49.5 degree angle, if you draw a right triangle with a 49.5 degree angle, then it seems that your hypotenuse is always going to be about 1.34 times your side that's opposite the 49.5 degree angle, right? This is my way of representing it in a very informal equation, right? Or with our first example here, if you got a right triangle with a 27 degree angle, then it means that your hypotenuse is always going to be about 2.2 times your side that's opposite the 27 degree angle. So and I encourage you to draw more right triangles with different angles and try it for yourself and see the same pattern emerge, as long as you draw your right triangles carefully and make your measurements as accurately as you can. Now, if you are a mathematician and you discover such a consistent pattern, you want to make a function to represent it and generalize it beyond these specific values. You will want the function to encapsulate these numbers in it, such that when the function should tell you that when you draw a right triangle with 27 degrees, so if you feed that as input into your some kind of function here, then your hypotenuse will be about 2.2 times longer than the side opposite the 27 degree angle, right? Or in more of a formal mathematical form, you could say that your function, right, and you input 27 degrees equals 2.2, and this 2.2 means the ratio of the hypotenuse divided by the side opposite 27 degrees. And in general, when you draw a right triangle with an x degree angle, the function, once you feed it into the function, it should tell you that the right triangle will have a hypotenuse that's y times longer than the side opposite the x degree angle. Right, so y will equal to the hypotenuse divided by the side opposite the x degree angle in a generalized form. And this is where we hit the trigonometric functions officially. And this function, in specific, that I've been talking about, has a name. It's not called func, right? It's actually called the cosecant function. Cosecant as in cosecant, like this, but abbreviated CS. See? So what you will actually write, you will write cosecant at x degrees equals y. Or with the specific cases we're talking about, cosecant of 27 degrees equals to, well, about 2.2. And then cosecant of 49.5, what's that other angle? That is approximately 1.34. Now, you should know that the cosecant function isn't very popular. It has a much more well-known counterpart called the sine function that tells you exactly the same information as cosecant, except in a different way. So instead of telling you, for example here with this right triangle, instead of telling you how many times longer the hypotenuse is than this side opposite the 27-degree angle, the sine function will tell you how many times longer this side is than the hypotenuse. So for example here, we know for the 27-degree, for the right triangle with a 27-degree angle, right, the hypotenuse is 2.2 times the side opposite the 27-degree angle. Well, we can just do a little bit of algebra here to rearrange for what the sine function is trying to tell us. So if we multiply both sides here by 1 over 2.2, right? Multiply this side, multiply this side. So what we will get is that the hypotenuse times 1 over 2.2 equals the side opposite the 27-degree angle. Okay, and let's see what is 1 over 2.2. That is about 0.45 repeating. So we say that basically the side opposite the hypotenuse, the side opposite the 27-degree angle is about 0.4545 times this hypotenuse. Okay, and if this sounds a little bit strange to you, to say something is 0.45 times another length, you can also think of this as a percentage if it helps. So if we rearrange here, so we get 0.44545 equals to the side opposite the 27-degree angle over the hypotenuse, right? So this is basically, the same information could be said that the side opposite the 27-degree angle is 45.45% of the hypotenuse, if that helps you see it more clearly. And that is what the sine function tells you. So we will write, and the abbreviation for sine would be sin. It's not sin, it's sine. It's just abbreviation. So we say sine of 27 degrees equals to 0.4545. And that means the ratio between side opposite 27-degree angle over the hypotenuse. Well, now you might have realized that our calculator, it has a sine button there. Okay, not a sin button, it has a sine button. Well, so our calculator actually stores a value for what sine of 27 degrees is as well. Because remember here, for us, sine of 27 degrees, we got 0.4545. That is from what we measured. Using rulers on a piece of paper, we measured the sine of 27 degrees should be 0.4545, meaning the side opposite the 27-degree angle is 0.4545 times the hypotenuse. Well, because, as I said, my imperfections with my drawing and my measuring, this isn't the perfect value, but our calculator stores a much more accurate value that if math is what it is, it should be very close to 0.4545. Let's see what it says. 0.4540 rounded to 4 decimal places. So here, so I should actually put roughly equal sign here. So our calculator, the sine of 27 degrees goes to 0.4540. That's actually very, very close. Right? Good stuff. I did do my measurements very carefully here, so I'm happy to see I got a value very close to the calculator. And that is here trigonometry shown through just playing around on a piece of paper. Now let's check with our 49.5 degree angle here, remember? So the right triangle with a 49.5 degree angle, remember that we said the hypotenuse is 1.34 times the side opposite the 49.5 degree angle. Well, if we rearrange here, we can say, so this is, again, so we say cosecant of 49.5 degrees equals 1.34. Let's find out what sine would say. Sine would say exactly the reciprocal of that, basically hypotenuse times, let's see, 1 divided by 1.34. What is that? That is 0.7463. I'm going to just round to 4 decimal places. Okay, equals the side. So the side opposite the 49.5 degree angle is exactly 0.7463 times the length of the hypotenuse. So we expect that sine of 49.5. So this function tells us that if we draw a right triangle with a 49.5 degree angle, then the ratio between the side opposite the 49.5 degree angle and the hypotenuse will be 0.7463 equals the side opposite the angle divided by the hypotenuse. Okay, so this is the function with the input, this is the output, and this is what the output really means if you want to see it like that, and all of these are equal. Let's see what our calculator has to say about that. Okay, sine of 49.5, let's see, 0.7604. Okay, not as close as our other one, but yeah, as you can see, extremely close. Basically 0.75 here and 0.76 here. See, this is what really gets me about trigonometry, just how cool it is that such a pattern holds on a plain sheet of paper like this. Like, there's no software program encoded in the paper, it's just a piece of paper, and nobody's controlling us to draw triangles in this way. The truth simply is that we cannot draw a right triangle with a 49.5 degree angle and have this side not be, roughly 0.7, what is it? My calculator, 0.76 times the hypotenuse. Now, obviously, a triangle has three sides, and sine and cosecant only tells you the ratio between the hypotenuse and this side opposite the angle of interest. But what about this side that's beside the angle of interest and its relationship with the hypotenuse? Well, there are trigonometric functions to describe that as well, called secant and cosine. Now, secant tells you how many times longer the hypotenuse is than this side beside the angle of interest. So what you would say is that the secant function, and you input some x degrees, it tells you how many times longer the hypotenuse is than the side beside the x degree angle in a right triangle. And cosine tells you, again, the same information, but in a different way. If you feed x degrees into a cosine function, it tells you how many times longer the side beside the x degree angle is than the hypotenuse. Okay, and in fact, let's repeat what we've done so far to discover secant and cosine again, right? Let's go back to the angles that we drew before and measure this side, the third side that we didn't measure yet. Okay, and let's see if what pattern we can see for cosine and secant. Okay, so let's see. I'm gonna measure this long side over here. We have about 6.9. Yeah, I was saying nice, exactly 6.9 centimeters for the long side here. And then let's see what this shorter side is. So, let's see, this is 4.2. Wow. I say 4.15. Oh, okay, so here, the shorter side is 4.15 centimeters. And also let's get the third side of this triangle that we drew. And remember, all these three triangles, they are right triangles that also have a 27-degree angle. So this one is 3.45. I would estimate it to be 3.45 centimeters. All right, now let's see. We're gonna skip the secant ratio, the secant function, and we're just gonna go directly to cosine because that is again, just like sine, cosine is the more popular version of conveying this information. Okay, so basically, let's see, 3.45 over 3.95 here. That's going to tell us how many times longer the side beside the 27-degree angle is than the hypotenuse, right? Or as I said before, you can visualize it as a percentage. So what percent of the side beside the 27-degree angle is then of the hypotenuse? Okay, and we have here 0.8734 if I round. If I want to extend up to 4 decimal places. Okay, and let's see for this larger triangle here, what would that be? So here we have 6.9 over the hypotenuse, which is 7.8. This is equal to 0.8846. And if we come up to this smaller triangle embedded in the bigger one, let's see, we have 4.15 over 4.65. Okay, and we have 0.8925. Right, so look at that. So here are our new ratios. You can realize that they are, again, very suspiciously similar because they are the output of the cosine function when you input 27 degrees to it. Again, notice how our calculator has a cosine function, right? And let's see, if we put in 27 degrees, what do we have? 0.89, pretty much exactly 0.891. So that is, again, what the cosine function is trying to tell you. It's trying to tell you the relationship between the adjacent side and the hypotenuse. Right? And so we can roughly equate all of these to cos of 27 degrees. I have no room. And then you can further investigate the ratios between the two sides opposite the angle of interest and the side beside the angle of interest and see what that ratio is, and from there you will find tangent and cotangent. So actually we have all the values here with us, so it should be pretty straightforward. So tangent is basically what is, we would say, here, let me get a new piece of paper. Okay. So tangent, and shorthand is tan of an angle, tells you how much longer is the side opposite the x degree angle over the side beside the x degree angle. And you can see how cosine, sine, and tangent takes care of all the possible relationships you can have within a right triangle. So here for a 27 degree angle, if that's our angle of interest, then the side opposite the 27 degree angle is 1.8. And the side beside the 27 degree angle is 3.45. Let's see, what do we have here? 1.8 divided by 3.45 is about 0.5217. Right, and let's see what our calculator, and so remember this is what we got from our raw measurements on a plain sheet of paper. Let's see what the calculator tells us tan of 27 degrees is. Well, that says it's 0.5095, so roughly 0.51, and here's roughly 0.52. Look at that, and we can further confirm with our two right triangles here, right? So for the bigger one, we have the side opposite the 27 degree angle is 3.55. The side beside the 27 degree angle is 6.9. Nope. And I'm expecting that to be roughly 0.5. Right? And as you can see, it's 0.5145. And as for the smaller triangle embedded in the bigger one, the opposite side is 2.1. The side beside 27 degree angle is 4.15. And here we have for 0.506. Again, tan of 27 degrees in the ideal state is 0.5095. And I encourage you to try this again with all the other triangles you might have drawn within this exercise, or draw more right triangles yourself and see these patterns emerge again. Through this video, I hope that you feel like you totally could have discovered trigonometry yourself if you really got your hands dirty with triangles. And it is too bad we don't get enough opportunities to experience the straightforward, simple beauty of geometry like this. In fact, this is my first time using protractors and rulers to this extent in many years. So I encourage us all to ground ourselves more with these kind of hands-on playing around of whatever new math concepts we might come across next. Playing around with specific values and truly understand what the generalizations and formulas are trying to tell us. To get started, at least with geometric things, all you need is a simple piece of paper and a pencil.